Hi everyone. Today we're going to talk about solving radical equations. Okay, this is chapter 10-4 in the book. First of all, the radical equation or a radical function is just an equation that has a radical sign in it. And under that radical sign, the radicand contains variables. Now, the easiest and simplest radical function that we can come up with is f of x is equal to radical x, or y is equal to radical x, right here. And I plotted that out. When x is 0, so was y. When x was 1, y was 1. When x was 4, the square root of 4 is 2. The square root of 9 is 3. And the square root of 16 is 4. And that gave me enough points to draw a pretty decent graph. Notice how this graph is always going upwards. There's no point at anywhere along this graph where this graph will start to go down. It's always going to be going up. We call that monotonic. And because it's going upwards, we're going to say it's monotonic increasing. Now, there are other graphs that are monotonic decreasing. In other words, it never changes directions. It's always headed with a positive slope. Even if the slope becomes very, very small, it's still a positive number. The other thing to notice about this function, this y is equal to f of x, y is equal to f of x is equal to radical x, is that we have a restricted range and domain. Notice that our domain, what we can put into the radicand x, has to be greater than or equal to 0. So the graph starts at x is equal to 0 and increases. There's no negative x. Also, the same is true for y. The square root of 0 is 0. That's the lowest possible y value right down here. And as x gets bigger, y gets bigger. That's what makes it monotonic too. Okay, we can take that graph and move it up and down and left and right, just like we did with polynomials. And actually, probably the best comparison would be the square root function. Now, when we take a constant and add it to a function, it just moves it up and down. It's an offset. So to put in an offset, I will just take y is equal to square root of x and add 1. And that takes the graph, and notice now, it used to be down here, and it's been pushed up by 1. Over here was pushing it down by 2 units. We take the original graph and push it downwards by -2 units. And of course, I left a question here. What is that x-intercept? In other words, that's where y is equal to 0. So this becomes 0 is the square root of x minus 2. That means the square root of x is equal to 2. And I'll leave it at there for you. Square root of x equals 2. And you can tell me what x is. Okay, a phase shift. That was when we moved the graph left and right. To do that, we're going to add a constant to the radicand. Notice up above, we added a constant to the function. Now we're going to add a constant inside the radical sign to the radicand itself. So if I add 1, ask yourself, what value does x have to be for y to be 0? Well, x has to be -1. -1 plus 1 is 0. So y will be 0 when x is -1. And that'll give us our starting point. Notice that x is -1, y is 0 right there at the red dot. And then the whole graph is the same thing. It's just been pushed to the left by 1 unit. Or I can push it to the right over here. The square root of x minus 2, x has to be +2 for this to be 0. So when x is +2, y is 0, and the whole graph was pushed towards the right in that direction from where we started by 2 units. Notice my domains have changed a bit because of this shifting, because of this phase shifting. You can also multiply these. For instance, if I just have y is equal to radical x and I multiply it by 3, well, it takes every value and multiplies it by 3. Whatever this was, well, that is 3 times it. So it stretches it out just like every other function that we've seen. And of course, we can put all these together in the end. We can have a phase shift. We can have it stretched out. And we can have it offset. And what does this look like? We'll leave that for you too. Okay, so let's get back to y is equal to f of x, because we want to start solving these types of equations. So here's a simple one. Radical x is equal to 3. I think about that for a bit. It's 9. X has to be 9, of course. But let's do this mathematically. So to get rid of the radical sign, I square each side. So that's what I did right here. And of course, if I square one side, I have to square the other. So the square root of x squared is just plain old x, and 3 squared, of course, is 9. And there's my mathematical justification for coming up with my answer of 9. But now we have a technique. Notice how we get the radical all by itself. We square each side. That gets rid of the radical sign. And hopefully that gives us our answer. So let's try something a little more complicated, like radical x plus 2 is equal to 5. Once again, I'm going to square each side. 5 squared is 25. X plus 2, radical x plus 2 squared is just x plus 2. I get x plus 2 is 25 and x is 23. We got to make sure we check these though. So I'm going to take x is 23 and put it back up in here into x. So 23 plus 2 is 25. The square root of 25 is 5, and that's exactly what we expected it to be. The second equation, the second function over here that we're trying to solve, same idea, square each side, find out x, and check your answer. Checking your answer is ultra important because when you square each side, like you did right here or you did right here, that can take things that are negative and turn them into something that's positive and introduce an error unbeknownst to you. So check your answers. So here's a couple more examples. All right, so the first thing I want to do is isolate the radical. I have plus 7 here, so I'm going to take away 7 from each side. And now I just have radical 3x plus 2 is equal to 6. Once again, square each side, solve for x. We get x is 11 and 1/3. Plug it in, make sure that it works. Now, sometimes you might not get any answer because the square root of anything has to be greater than or equal to 0. As long as anything is a real number. You'll see in Algebra 2 that when we get into imaginary numbers, that rule can be violated. But for now, we're dealing with real numbers, so everything has to be greater than or equal to 0. So if I have, for instance, the square root of x is equal to -5, nothing's going to work there. That is just not possible. So for instance, if I have radical 5x plus 7, then plus 10 is equal to 6. Take away 10 from each side. 6 minus 10 is -4, and I have a radical that's negative, which means there is no solution. So we've seen that the way to go about this is to isolate the radical and then square each side. Now, what if you can't isolate the radical? For instance, I have a radical on each side. I suppose I could subtract one, but then I'd have 2 radicals, one minus the other is equal to 0. And then when I square each side, it's going to be a mess. But this one's pretty simple because if I square this side and this side, both of those radicals are going to disappear. So let's see what happens. Square each side, 3x minus 6 is equal to x plus 23. It turns out that x is 14.5. My check is below. Sure enough, it works just fine. Sometimes life isn't that simple though. What if I have a radical on each side, right here and right here, but also plus some constant? Now I still have to square each side. So I do. Notice that radical x plus 1, everything squared, is equal to x plus 1 plus 2 radical x. That's all done right over here. Okay, now we're going to isolate everything, combine up like terms. I take away x from each side, that got rid of the 2 x's. Let's see, I'm going to take away 1 from each side. That turns 7 minus 1 into 6. 6 is 2 radical x. Divide each side by 2, and I get x is 9. Okay, I get 3 as radical x, and of course x is 9. Now we got to make sure that this works. We're going to take x is 9, plug it back in up top. Radical 9 plus 7 is radical 16. Radical 9 is 3, plus 1 is just 1, so 3 plus 1 is 4, and radical 16 is 4, and that worked just fine. Notice, though, I had to square each side twice. I did it one here, and right there was my second time. And that's because I had 2 radical signs, and I wasn't able to square each side to get rid of them because I had this plus 1 out there. So you can still do it. It just takes you a few more steps. Now, these ideas work for cube roots and fourth roots, whatever roots you have. So let's say we're dealing with cube roots. To get rid of a cube root, I would cube each side. If it was a fourth root, I would raise each side to the fourth power. So this is called my index number. With square roots, it's 2, but we don't usually write it. But anything other than 2, we have to write. So this is a cube root. The cube root of x minus 6 is equal to 2. Now to get rid of the cube root, I'm going to cube each side. I cube the left side, I cube the right side. I get x minus 6 is equal to 8, which gives me x is 14. We're going to make sure that that worked. I'm going to take 14, plug it into x. 14 minus 6, that's 8. The cube root of 8 is 2, and we are good. Funny thing about cube roots, though, is that the radicand can be negative. If you notice the work that's done over here on the right, once again, we cubed each side. We got x was negative 2. Notice when I check, I have the cube root of negative 8. My radicand is negative, but that's okay. That is okay as long as your index number is odd. Now, I mentioned before, sometimes when you square each side, you can introduce an error, which is kind of a bummer because you haven't made a mistake in any of your math, yet your answer does not work. It's wrong. So you have to get rid of it. And the only way you're going to know to get rid of it is to check it. That is it. So here we go. Here's some examples of some problems where all the math worked out just fine, except for the fact the answer does not work. So here we go. I'm going to solve radical x plus 1 is equal to x minus 1. So once again, I square each side. X minus 1 squared is x squared minus 2x plus 1. And collect up all my like terms. I can factor that guy. X times x is x squared. X times minus 3x. So that means if this is 0, either x is 0 or x is 3. Okay. So I need to check though. So let's check x is 3. Take x is 3, plug it back in. 3 plus 1, the square root of 3 plus 1 is equal to 3 minus 1. And of course, the radical 4 is equal to 2, and that works fine. So x is equal to 3 is okay. X is equal to 0. Let's plug that in. I have radical 0 plus 1, which is just radical 1. But over here on the right, 0 minus 1 is negative 1. And I have a radical equal to something negative. Can't do that. So we only have one answer. And that is x is equal to 3. We have to eliminate x is 0 from the answer list. Okay, here's another one. Once again, we're going to square each side, collect up our like terms. So here we go, we square each side, collect up all our like terms, and we solve the quadratic. Now, this quadratic can actually be factored, or you can use the quadratic formula. Either way, you're going to get 2 answers for x, negative 2/3 and 2. Check each one. When x is minus 2/3, notice that 2x minus 1, when you plug in minus 2/3 is minus 4/3 minus 1, which is negative. So I'm not even going to go any further. I have the square root of something is negative, and that can't happen. So minus 2/3 is off the list, but we still have to check 2. Plug in 2, everything works. So we only have one answer. X is equal to 2. X was minus 2/3, was an extraneous solution. Okay, guys, that's it. Be good. Talk soon.